This is a video lecture for potential and kinetic energy. First off, we're going to divide energy a little bit into a couple of different camps. First camp will be potential energy. Second is kinetic. Now, potential has a lot of different branches underneath it. Potential is kind of a stored up energy. So you put potential into something by doing work. And you kind of store it up for later. Kinetic energy is energy associated with motion. Under potential energy, we can have several different types. The main one we're going to work with is gravitational potential energy. And that is when something is held at a height. But you could also have elastic potential energy when something is stretched or compressed like a spring or a rubber band. Chemical potential energy is extremely important because it's responsible for the energy storage in batteries or things like gasoline or other fuels that are burned. So you break those chemical bonds and that releases energy. Kinetic energy really just comes in one flavor, as we'll see in a little bit. Now, with potential energy, the base definition of that is simply an energy that is stored and can be used later. And as we discussed, there are several different forms. You might have gravitational potential energy, so this block up here being held at a height has some energy stored in gravity, so it's got potential energy. Something that gets stretched, like the rubber band on this paddle ball, stores up some energy. And our old friend the battery, which in this case has legs and a big smile, stores up energy and unleashes it when it undergoes chemical reaction. As usual, as you've learned, it's not enough to say that we have lots of potential energy or just a tiny bit. We actually want to quantify that with some sort of number, and that means we need to get a formula to calculate it. So let's picture a rock that's got its mass m and held up at some height. We saw that that will have a gravitational potential energy. That's the one we're concerned with. And the formula is PE, which is the gravitational potential energy here, is equal to m times g times h. And you know all of those pretty well. Potential energy we measure in joules. We named it after James Prescott Joule, who was an English physicist in the 19th century. He did a lot of the early work with energy. M is a mass in kilograms. We always basically use kilograms when we're making a measurement or making a calculation with mass. G is our friend, the acceleration of gravity. This is actually one that was missed a lot on the last test. It's not just gravity. It's not a force of gravity. G is the acceleration of gravity, which on Earth, as you'll recall, is 9.8 meters per second squared. And finally, H is the height of the object in question, which is measured in meters. Now, importantly, if we took each of these units, kilograms for mass, meters per second squared for acceleration of gravity, meters for height, and multiply all those together, we get our units, and that's equal to, if we have one of each, we have 1 kilogram meters squared. If you have a meter in the acceleration and another meter in the height, over second squared. That's really quite a mouthful to say, and it's not very useful to refer to something as having 50 kilogram meter per squared per second squared. It'd be hard to understand what that even meant. So we defined this as being equal to 1 joule. So just like a Newton in the last chapter was an abbreviation for what we get when we multiply mass times acceleration, joule is an abbreviation here. Kinetic energy is slightly different. That, as I said, was the energy an object has due to its motion. And it's got a different way to calculate it. We see here we've got some stored energy, potential energy, when the block is held up high, but as it's released, that changes into kinetic energy because it's moving. Kinetic energy is calculated as 1/2 mv squared. Kinetic energy is a KE, and all energies we're going to measure in joules. One energy of kinetic energy is the same amount as one energy of potential energy. M is our mass in kilograms again, and V is our old friend velocity in meters per second. Now notice that that's velocity squared.
So you would take that velocity, square it first, and then multiply by m and 1/2 to find the kinetic energy. There's one really important physical law that governs all of this energy, and that is the law of conservation of energy. What the law of conservation of energy states is that energy can never be created or destroyed, but it is allowed to change form. So it can change from potential to kinetic, and that's okay. So a couple of examples when this might occur is a cart at the top of a ramp has a bunch of potential energy, but when it's released, it goes down the ramp. As its height gets lower and lower, it loses potential energy. But that energy just doesn't disappear. It's actually transferred into kinetic energy. So that by the time it gets down to the bottom of the ramp, it will have the same amount of kinetic energy as it had in potential energy up at the top. Now, a car with speed has some kinetic energy. Let's say it's going up a ramp. Well, as it goes up, it's going to slow down, assuming it's coasting. So it's going to be losing kinetic energy. But it will gain potential energy because it will be going up higher and higher. And the amount that it loses in kinetic is the same amount of energy that it gains in potential. So let's do a couple of calculation examples. First, we've got a 0.25 kilogram car that's sitting on a ramp that's 1 meter above a table. Want to figure out how much potential energy it has. Well, we know potential energy is equal to the mass times the acceleration of gravity times its height. We know mass is given in the problem as 0.25 kilograms. We know g is the acceleration of gravity on Earth. It's 9.8 meters per second squared. And we know the height that's given. It's up on top of the ramp, and it's 1 meter above the tabletop. So all we have to do to figure out potential energy is multiply those together. Multiplying the numbers together, 0.25 times 9.8 times 1 gives me 2.45. The unit-wise, we've got kilograms times meters per second squared times meters. We abbreviate that as the joules. So there's our potential energy. Now, the second question is, as it's released and goes down rolls down the ramp to the table, how much kinetic energy does it have when it reaches a table? A really important thing, the point of the law of conservation of energy states that it's going to have the same amount of energy all the way down. It's not going to gain, no energy is going to be created or lost during this. It will just change forms. So as it goes down, the height is lower and lower. So it's losing potential energy, but it'll gain the same amount of energy as kinetic. So it's just transferring. Down at the bottom, all of that potential energy is gone. Meaning that whatever it had at the top as potential energy is now completely converted to kinetic energy at the bottom. So the kinetic energy at the bottom of the ramp will be the same amount of energy that it had in potential at the top, namely 2.45 joules. Don't have to do any calculation on this. We just have to recognize and apply the law of conservation of energy. Now this can be useful though, because the last question is, how fast would the car be going as it got to the table? And for that, we have to use, whenever you see something like how fast and you're dealing with energy, that means kinetic energy. That's 1/2 times the car's mass times its velocity squared. We know the kinetic energy that it had at the bottom from the last problem, 2.45 joules. We know the mass for previous problems, 0.25 kilograms. We want to find the velocity. So we need to rearrange this equation and solve for v. First thing I notice is 1/2 times m times v squared. Let's get rid of the 1/2 first. We'll multiply both sides by 2. And we'll get rid of this one. Rewriting that, we have 2 times the kinetic energy equal to m times v squared. We got to get rid of the m next.
m times v, so we remove the m by dividing by m on both sides, and that was m squared. So we get 2 times kinetic energy over m is equal to our v squared. Now this is a little different. To get rid of a square there, you have to take the square root. So we're going to take the square root of both sides. The square root of v squared, the square root of anything squared, is that thing. So the square root of v squared is just v. And we have on the left side 2 times kinetic energy over m. It's very important when you're trying to figure this out that you figure out what's inside that radical, the square root sign, before taking the square root. So we actually have to take 2 times the kinetic energy divided by m first, figure that out, and then find out the square root. So let's do that. 2 times my kinetic energy of 2.45 joules divided by the mass of 0.25 kilograms. Figuring that out, I know that I've got, all right, 2 times the 2.45 divided by 0.25 works out to be 19.6. Now the units are weird, are stranger. Remember though that a joule is a kilogram times a meter squared over a second squared from the previous page. And if I divide that by kilograms, I cancel out those kilograms, and what's left is meters squared per second squared. If I take the square root of the number, 19.6, I get 4.43. Now, square root of m squared divided by s squared, I just knock off that little square, and I get meters per second, which is a very nice unit to measure a velocity. That concludes this video lecture.